Hey guys, this is the logic section of your philosophy class. This is the first part, 1.1, logic in the propositional calculus. I know that word propositional calculus looks a little ugly, but I promise it's not going to be as difficult as it seems. Just a little note at the beginning of this. Most of this part, what I'm going to be using, is from this book, An Introduction to Non-Classical Logic by Graham Priest. It's pretty heavy. If you're interested in some serious abuse, I highly recommend it. I don't really agree with a lot of what Graham Priest has to say, but his treatment of logic is excellent in this book. So if you're interested in it, you can get it off of Google Books right now. Let's go ahead and start though. Part 1, what is logic? So let me throw out a few examples first. The first one is this. Number 1, if you can read this, then you are literate. Number 2, you are reading this right now. 3, so you must be literate. So you kind of see how on this one, you can read this kind of corresponds to you are reading this. And you are literate kind of corresponds to you are literate here, right? Well, your ear might kind of pick up on this, but it sounds sort of like number 1 and number 2 lead to number 3, right? If you have this statement and you have this statement, then this one follows from them, whatever that means. That's sort of what we're doing in logic. Here's another example of the same kind of thing. Once again, I have, if you can read this, you're reading this, same thing, but instead of what I had before, which was you must be literate, now I'm putting you are a cactus. Why you're a cactus, I don't know. I came up with some of these examples totally arbitrarily, obviously. But you kind of see the same format, and I don't know if your ear could pick up on this, but these two things actually lead to this third one, just like the first two, right? Same format, same exact format that we had before, but you might be wondering, well, I'm not a cactus, so how does that work? Well, all I'm trying to show you here is same format shows you that these two lead to this, but that doesn't mean that all of these up here are true. If these are not true, then this will lead to a falsity, possibly, right? So you can have the format correct when you still have falsities. Now here's a case where you have true things, but you have no format, right? So if you can read this, then you are literate. Let me give my colors again. I kind of have a color fetish here. If you can read this, then you are literate. And there's blue, I think. You are literate. There. You are human. So this is something totally different, right? We use green, because green is totally different. If you can read this, you are literate. You are human, so you must be literate. So these two don't seem to lead to this third one, even though all three of these statements are true, right? So what logic is worried about, we're not so much worried about this. We're not worried about when you have a false guy here, you have a false guy there. Philosophy is. When we talk about philosophy, we'll be very worried about that. But in logic, we're just worried about, did I set this up correctly so that this one follows from these two? Something like that. All right, now let me get really complicated on you. What is logic? Well, logic, by the way, this guy equals def, that means definition. So the definition of logic I will use is study of validity. Of course, the question is, what is validity? Validity are inferences that can be made in an object language. That probably doesn't help at all. An inference, by inference I mean what we were doing before, where you're saying, hey, I have these two things that I know, and here's this third thing I can get from those two things, right? So an inference is something like that. You can infer. Inferences that can be made in an object language. What is an object language? Object language is the language you're studying, right? It's the object that you're studying. And it's a formal language that you're studying. And by formal language, I mean it is well-defined vocabulary and grammar. It has these two things. By well-defined vocabulary, what I mean is something like, you know what all the symbols either mean or could mean, right? So if you have symbols that stand for things, then that's fine, but you got to know what they could stand for. So like if I have, a variable like x in math, I know that can stand for numbers, whatever. That's well-defined. I know it cannot stand for socks, right? So well-defined vocabulary, you know what everything means or could mean, and grammar are just the rules that help you make well-formed formulas, right? So something that makes sense. So I can't say runs, jumps, walks. I have to have a subject and a verb in order to make any kind of sense in English. So that's what a formal language is. You have all that stuff set up, so you know all the stuff that you can make from it. I know runs, jumps, walks is not going to be a correct sentence, and I know that Bob buys a donut is. I apologize for my examples. I don't know. Anyway, meta language. This is less important, by the way, than this stuff. But just in case you were wondering, you might be thinking, okay, so we're talking about all this logic stuff. We're studying logic. We're studying how this stuff works. But don't we have to sort of use logic to talk about logic? I mean, aren't I sort of reasoning through these kinds of things? Yeah, that's very true. Absolutely true. And for that reason, people have defined meta language as the language you're talking about, the language in. You kind of can't get around that, right? Like you can't talk about language without talking with language. So it's something that we could talk about in class, the philosophy of that. But most people agree that it works. What about validity? What kind of types of validities are there? Well, there are two major types, and these are the two types that we'll be worried about at all. The first one is semantic validity. I know these words are ugly. By semantic, all I really mean is like meaning validity. You're worried about true or false. I know I said not worried about true or false before, but what I'm saying is you're worried about if A is true. You're not worried about if A is really true, but if A is true, then is B true, something like that. So every interpretation that makes all the premises true makes the conclusion true. If we look back here and I see something like this and I say, okay, if I make this one true and I make this one true and I make this one true, can this be false? Well, no. If you make these all true, then this one can't be false. But if you look at this one, if you make this one true and you make this one true and you make this one true, can this be false? Yeah, it can actually. Because if you can't read this, then you might not be literate, right? So that's not valid. That's what I'm talking about. Proof theoretic validity, however, is a little different. Proof theoretic validity is where you just have a bunch of rules that you lay down, and does the conclusion follow based on those rules, right? So if I say you can only have I don't know, shoot. I can't think of a good example without actually getting into it. But basically, you're just following rules and not worrying about true or false kinds of things. And you'll see that in the next video for sure. All right, propositional calculus. What does that mean? Well, proposition, really all that means is like a statement, right? Puppies are fun, something like that. And here you have some symbols for it. We're going to use lowercase letters. P0, P1, P2 can all be propositional parameters. Really, we're going to be using more of these things down here. Oh, where did my pen go? Oh, here it is. We're going to be using more of these things down here. Lowercase p, lowercase q, lowercase r. Those are propositional parameters. When they're different letters, though, they're going to be different propositional parameters. So p might be puppies are fun, but q cannot be puppies are fun. It must be baseball games are boring. I don't know, something like that. They're not boring. I like baseball, by the way. So we will have those for propositions. Those are the statements, and then these things are going to be used to connect statements together to make formulas. All right. Now, all of these have all started off from things in English that they symbolized, and we've learned, through philosophy of language, that English is kind of messy and doesn't always obey its own rules. So these have kind of become a little detached from English, but still this is kind of what they mean. All right, this gentleman right here kind of means not. So if you were to say that guy, that means not P. So if P is puppies are fun, then it's not true that puppies are fun. Right? This guy right here means something like and. It conjoins two propositions. So P and Q would mean puppies are fun, and I can't remember what Q is. Oh, baseball games are boring. I should not have chosen that. Promise you, if you're a baseball player, I like the Angels. So, disjunction, this little wedge right here, is something like or, but this is kind of confusing because we use the word or in a lot of different ways in English. But it's kind of like an or that would mean at least one of these two things are true. So if I say P or Q, I mean something like either puppies are fun, or baseball games are boring, or both maybe. At least one of these two things is true though, I know that. The material conditional. Now, I have some extra material on the hot and heated debates about this one. But it means something like if then. If you have P, then you have Q. So let's say if you have P, let's say P is you are literate and Q is you can read this. If you have P, then you can, if you are literate, then you can read this. Right? So that's kind of what it means. Really what it means is if you have this one, you're going to have this one for sure. That's what it means. These three lines right here is material equivalence. What it means is something like if and only if in math. So in other words, if I have this guy, P if and only if Q, what that means is if I have one of these guys, either one of them, I have to have the other one. And if I don't have one of them, I can't have the other one. So something like if it is a triangle, then it's, it's a triangle if and only if it is a three-sided figure. That means if it's a three-sided figure, it's not then it's a triangle, and if it's a triangle, then it's a three-sided figure. And if it's not one of those two things, it's not the other one. And we'll use commas just to separate these kinds of things out. So let's say P if and only if Q, and I want to say also, by the way, R, but that has nothing to do with these guys. I'm just going to use a comma to separate those, just like kind of like in English. Alright, a few more symbols. These capital letters right here we're going to use to symbolize formulas. So the lowercase letters are going to be statements, those propositions. The capital letters are going to be used to symbolize any of these guys that we made up here. And possibly these guys too. Right? So A could equal P if I wanted to. Or it could equal P and Q. If I wanted to, I could even make it equal something like capital B or capital C, right? I could combine formulas to make a new formula. It's kind of like math, right? I could say 1, I could say 1 plus 1, x could equal 1, x could equal 1 plus 1, x could equal, 1 plus 1 plus 1 plus 1. I can make all kinds of crazy formulas if I want to. And these guys, these capital Greek letters, are going to symbolize sets of formulas. So now a set of formula can be a lot of different things. It could be sets can be empty, right? I could have nothing. So let's say sigma here equals nothing. Or it could equal just a proposition, right? Because those could be formulas. Or it could equal a formula. Let's say I want my formula to be A or B. It could just be A, it could be A or B. Or it could equal sets like these right here. So I could say A, comma, B and C. So it can symbolize a lot more than just these. That's why we're labeling these guys just because we want to be able to get these things down here. Like what if I have formulas that are not connected, that they're not one formula? That's why we even talk about these things down here. Yeah, there you go. So last thing we'll talk about is the grammar. A well-formed formula, kind of like what I alluded to before, what that really means is just something that makes sense. So things that make sense in logic, all and only, or in the propositional calculus, excuse me. That's what we've been talking about so far. All and only the strings of symbols that can be generated recursively, that means by applying the same thing over and over again to itself, the same rules, from the propositional parameters by the following rule. If A and B are formulas, so are not A and B, A or B, if A then B, and A if and only if B. Sorry, I'm trying to find this pen. So if these guys are legitimate, then any of these are legitimate, and recursively you can keep adding and adding the same way. So let's say A is legitimate, then not A is legitimate. And also, let's say B is legitimate, then not A and B are legitimate. And I could even say not A and B are legitimate, or I could say not A and B if and only if B. So I could keep applying this and have, you know, potentially an infinite sized formula. That makes sense in this object language, in this propositional calculus. That's it for propositional calculus introduction. I have there's a different way to do this, and I'll make it a bonus video. In other words, if you haven't had enough abuse yet and you want to get bored to tears a little bit more, you can watch that. But if you don't want to, you can skip that one and go on to the next video.